So we can expand this idea of exponential growth to also encompass exponential decay. And it is something that most people just know almost intuitively from having seen the price of something diminish over time, or learning in school about carbon dating or something, where you have some initial value and then after some period of time it's half that value, same period of time it's half that value, same period of time it's half that value. You get an exponential decay curve like this, and this also can be modeled by some amount is an initial amount, e to the RT, but that rate is going to be a negative value. If you're losing, if automobiles often are said to lose about 7% per year, it would be minus 0.07, and then you could model that over time. And you could use that rule of 72 to estimate when your car might be worth half its value. Okay, so exponential growth, exponential decay, all based on this same equation. Okay, so then if we go to Newton's law of cooling, you'll see that this is really the same concept. We have a camera that's got a little bit crooked there. We can think of taking something out of an oven, or something that's hot, or something you've heated up and it's cooling off. It's going to cool off, but it's not going to cool off to zero. Absolute zero would be too cold. But it's going to cool off to whatever the ambient temperature or the room temperature is. So if you think about this, delta T is that temperature change from the initial temperature to room temperature. If you build the decay model off of that, or the growth model off of that, it's really quite simple, okay? So the change in temperature is the temperature of the thing that you've taken out of. If we're talking about cooling, it's going to be hotter, so we subtract the room temperature, and then we can build an equation for time variation of that temperature as the temperature of this object as it cools off over time is going to be your room temperature plus that delta T as it's decaying, and R there will be negative. So this is like the value of your car, or the value of carbon-14, that's decaying, and when it decays down to nothing, you're at room temperature. All right, so just get comfortable thinking about that way. So here's an example. You've got hot coffee that's coming out, Celsius, centigrade, near boiling, 100 degrees, so just a little bit cooler than boiling, with a room temperature of 20 degrees, okay? So after 5 minutes, you know it's cooled off to 86 degrees, okay? Well, it would not be correct to assume that after 5 more minutes, it would have cooled off another, 7 degrees, okay? It is going to go by diminishing returns there as it decays. How long until it reaches 70 degrees? And then how hot is the coffee after 20 minutes? All right, so what we do is we just set up an equation and solve that. So it's our difference in temperature from coming out at 93 and going down to 20 degrees. That's a change in 73 degrees. So we know that it's going to decay 73 degrees down to that 20 degree mark. Now I just need to solve this. So if I put in the values, put in my 86 degrees, do the math here, and then I'm just going to divide by 73, and I take the ln of both sides, and I'm going to get the ln of 66 over 73 is equal to 5r. When I divide by 5, I'm going to get an r value of 0.0256. If you're doing this on a calculator, you can store that as alpha A, and then plug it back into the equation. Here then, if I've got 70 degrees is equal to 20, I've got, over time, here's my equation, so I'm just going to start, plug in my values and then solve. There it is, I've got it plugged in here, so it's 73 e to the negative 0.0256. I've subtracted 20 from both sides, and then I divide that by 50 by 73. I take the ln. I'm going to get a value which I then divide by my rate of decay, and I get 15.859 minutes, okay? A little bit of a clumsy explanation, but that's how you do it. You can go through it yourself. How hot is it coffee after 20 minutes? Again, you're going to go to your equation This is going to be your minus 0.0256. And what we're going to say is how long will it be if I don't know the temperature, and then I do this times 20, and then I work that all out. It turns out that's going to be very close to 68.78 degrees after 20 minutes. Okay, so know that equation. Now here's another example. This is Newton's law of heating, all right, because I'm taking something and putting it into an oven and I'm heating it up. So a turkey is put into an oven at 400 degrees, so that's the ambient temperature. So this is cooler than that. So the turkey's obviously getting cooked, it's warming up. It warms up rapidly from the room temperature. This time we're in Fahrenheit because we're used to these temperatures here. Warms up to 150 in 85 minutes. Okay, how long until it is done? Well, to be safe to consume, you should heat turkey to about 165 degrees. So we again have an equation where we're taking that oven temperature and we're taking away the temperature differential. That's our delta T. And so I wind up with this equation like this. I sub in my values that the temperature difference in this case is 328 degrees. Initially, when we first put it in, when that's 0, we take away all of that. So we're down at the room temperature, 72 degrees, and then it decays upwards to that ambient temperature of the oven. Okay, so it's all about your perspective. And once you think about this delta T, I think it's relatively easy to conceive of a curve like this rising, or up here, a curve like this falling. All right. Anyway, so the math is quite similar. I just plug in what I know. I work through very carefully to solve it, where I say how long will it be till it's done at 165. I take away 400. I'll get a negative 235. Then I divide by a negative 328. That's less than 1. The negatives cancel, but because it's less than 1, I get a log of a number less than 1. I'll get a negative value, and there's my T. When I divide both sides, when I find this, I get a negative. When I divide by this value, I'll get that T of 104 minutes. So a little bit less than 2 hours for it to warm all the way up. Okay. Final example here is the murder mystery. We find at 5 p.m. A dead body, and the murder has happened at some unknown time, but the body is already cooled off from 98.6 to 90.6, so it's cooled off 8 degrees. We wait some amount of time that we know, and we take the temperature again by having two equations with Newton's law of cooling. We can then solve for the unknown. All right, so notice how this is set up. Here's the two temperature values. The delta from 98.6 to room temperature is 68.6 degrees. The room temperature is 68.6 degrees. The delta then from 98.6 is 30 degrees. So that's that change in temperature as this decays from 98.6 down 30 degrees to get to room temperature. So this is one equation. Here's the other equation set up. Now notice that my initial time is just T. I don't know what that is, but I do know that my second time is 4 hours later. So that's crucial. You can't call that T1 and T2. You'd have two unknowns, but you can relate this by saying, I know that this is 4 hours later. So if you think through the math, I can subtract the 68 from both sides. I get these two equations here. 22 is equal to the 30e to the kt, and then 14 here is equal to 30e to the kt plus 4. Remember, if I distribute that in, I then have kt plus 4k, and because of the nature of exponentials, that's no different than if I had 30e to the kt times e to the 4k. Okay, so this is a little trick for solving these, and take a moment, pause the camera, and look at these, okay? Because what it means is that I can use this to solve for the equation by canceling those out, all right? So if I divide this by 14 by e to the kt, they're both equal to my circled 30 e to the kt's. And so this then, they are equal to each other. And then I go over here and I say, oh, because they're equal to each other, I can now solve for k. So the math is quite simple after that. So work through this little trick here and see how that works, but it is a nifty little way of solving it quickly. So I then, if I do the little algebra switcheroo here, I get 7 over 11. I've canceled the 2, and it's equal to e to the 4k. Take the log, divide by 4. There's my k value. Okay. Once I have a k value, then I can plug it in here and use it to then work backwards in time, so that I know that the t value, when I plug everything in that I do know, I can plug in and find the t value here, and the t value winds up to be 6.7488. So that is a value that's 2 hours and 45 minutes. This is the value that's 2 hours and about 45 minutes before 5 p.m. or 2:15 p.m. in the afternoon. Okay? And it's possible, if you're curious, you can also check this on your calculator with the regression equation, and you can ignore the 68.6 degrees and just adjust it to be these 2 points and do a regression equation, and you'll get the same correct answer. All right? Good luck.